I come to this meeting not with a solution, but with another problem. A problem that possibly will be solved if you guys get your ducks straight and get the densities done properly. So this is my team. We started in 2018. And so the entire team, our work is we like to think of a computer as a microscope. And we'd like to believe that in days to come, a computational microscope and a real microscope will work hand in hand, will work together. So to do that, of course, as I said, so we start out with molecular dynamics simulations. So just a brief refresher of molecular dynamics. In molecular dynamics, how many of us has done molecular dynamics simulations in the room? Okay, a fair amount. So then we know, and for the ones who don't know then, that what you do is molecules, of course, are composed of electrons and nuclei. Electron is diffused across the nuclei. But what we choose to do is we say that let's take this diffused electronic cloud, convert that to springs with spring constants, and parameterize them. That's what you call force field parameters or molecular mechanics force fields. Once you have this force field parameters, now you can actually have a potential energy surface, a surface of energy, so you get to know for how much displacement in your atoms, what is the energy change. Normally we use harmonic potentials for these. And then once you have this potential, you simply solve Newton's laws of motion. Now, it turns out that classically Newton's laws are force equals mass times acceleration, which is the same in molecular regime, but you have noise there. That's what you call fluctuation dissipation theorem. Normally, that's the kind of noise that you see because molecules are noisy. So a part of your Newton's equation will have to incorporate noise. And essentially, noise controls temperature of the system. So you are essentially putting your system in a heat bath and then solving Newton's equation and hoping that you find some sort of a local minima, like a protein folding simulation. And we saw several of those in the previous slides. Me, through my training with Klaus Schulten and of course with Emma Tachkorshid, we developed this tool called NAMD, which is one of the molecular dynamics tools that is quite popular nowadays. There are of course others, Chromax, OpenMM, Amber. Okay, so now the big news for the molecular dynamics community is DOE has actually gotten the biggest computer in the world to the US. It resides in Oak Ridge. It's called Frontier, which is called an exascale computer. That would mean we would be able to solve 10 to the power 18 floating point operations, double precision, every second. Actually, yeah, every second, that's correct. So a question, what does the word the number 10 to the power 18 mean to anyone here? 10 to the power 18, what's the nearest number that you can think of? Let's say I'm a chemist, Avogadro's number, it's like micromolar solution. So 10 to the power 26 if every atom for small molecules. So a protein physicist, a protein structure person should think 10 to the power 18 atoms, right? Which would give, let's say, assuming that every protein has 350 amino acids and each amino acid has 20 residues roughly, that's 10 to the power 15 proteins. How much is the density of a cell, the protein density of a cell? Any ideas? Actually, it's a controversial number, but came out in Cell actually a couple of years, 3 years back. 3 to 4 million proteins per micrometer cubed. What that means is 10 to the power 15 proteins would then mean like a millimeter cubed of cell, simulated in 1 second. So actually molecular dynamics has some hope. It's not that hopeless. But the problem is the following. We can do, in principle, we can end up simulating billions of atoms possibly, and there's memory issues. There's this paper that came out in PNAS, which says that the time to resolve, the time on CPUs to resolve a real biological event, T real being real biological event, delta being the smallest time step of a molecular dynamics simulation, V being the number of flops on the machine. They came up with a formula. According to that, 10 to the power 9, like a 3 billion atom system, which is like, let's say, a small bacterial cell, a piece of that, will take 10 to the power 9 years to figure out dynamics that is 2 hours worth long. Biological relevant dynamics can be 2 hours long. So of course, what you can do is you can say, fine, I don't want to do 2 hours. I can make this milliseconds. It goes down. How many? 1 hour has how many milliseconds? Like 10 to the power 5 milliseconds possibly. So essentially, this problem still for protein ends up becoming 10 years to solve really a millisecond scale protein with the best of computers today to figure out the Boltzmann distribution of the protein with brute force molecular dynamics simulations. and that kind of is a challenge. So that's where I think we hold the hand of the experimental community there. We want the experimental data to guide our simulations in a way, so that we can get over that 10 years barrier of a simulation. So that's why essentially we have a very self-centered view here in this community, that we want the experimental data to drive us towards where we go. And in doing so, if we can contribute something to the molecular, to the refinement of the models, I think we'll be able to. But the mindset was always this, that use experimental data in molecular dynamics to drive molecular dynamics and to get over this 10 years long old problem. Okay, so with that then, this is of course some of the things, and Cryo-EM is of course one of the data sets. I wanted to kind of highlight that Cryo-EM is one of the data sets that is used in molecular dynamics. There are data sets of different kinds: X-ray crystallography, tomography, bright field imaging. NMR is not there here, but molecular dynamics has this intersection with all these areas. And okay, so this is of course some of our work here. And okay, so this work, the work that I will talk today, the intersection of molecular dynamics with Cryo-EM, essentially began back in 2004 when someone called Charlie Brooks started working with elastic network models and densities. From my lineage, from my hierarchy, my advisor Klaus Schulten, together with Elisabeth Villa and of course Hakim Frank, they came up with a way of starting to fit structures to the densities. So let's say we have these three-dimensional densities. What do we do with that? We want to figure out biological structures. And so the first attempt at that was, you can see pretty low resolution densities. We purposefully keep this example, one of the first examples of taking a structure that is crystallographically resolved and fitting it to the density in order to kind of interpret this density with three-dimensional structures. So the interesting thing here is, you can see the potential that is used. So the potential, as I said, a force field is used, what we call U molecular dynamics, which is basically the springs that I just mentioned. A secondary structure restraint is often used because when you do these sort of fittings, the structure can break during your transition. So you want to make sure that whatever knowledge you have on the secondary structure, that is imposed. And finally, the important thing is UEM, which is what we do is, or what used to be done back in the day, is you literally take this density, and the density itself is a potential. So the derivative of the density is the force. So essentially, if I'm sliding on the surface of this density, the force that is the derivative of the density will draw me inside the density. So that was the original idea. This worked quite well till 2013. And then what happened is, of course, the resolution of these maps started changing, and the potential, like the potential that was derived out of the density, which was looking so smooth back in the day, started looking extremely jagged. There's a lot of features in these, and once you have these features, the problem that started happening is, as is molecular dynamics notorious for, the protein started getting stuck into very wrong density features because it got stuck into this local minima. Okay, and then of course there were papers written about MDFF written back in the day when I was just starting my postdoc by famous people, David Baker, for example, like that this should not happen. So then in order to address that, we came up with an idea from molecular dynamics, which is traditionally called simulated annealing. And then so you take this density and you start essentially low pass filter it and then gradually increase its resolution. So therefore, you basically start with a smoother surface and then gradually dig deeper into and make the surface more and more, introduce more features in this. That overcame this problem. This is of course showing simulated annealing. There was a replica exchange association with that, like where you don't just go in one direction in the density. You can go back and forth between high resolution and low resolution till you fix this problem. This problem had been duly addressed 5 years back. With that, of course, both backbones and side chains are well in place. One thing that we started realizing then, that was when we started thinking of there is a statistical significance of these kind of simulations. Normally, molecular dynamics is used like a fitting tool. Essentially, you have a function, you fit to it. There is no statistical significance to it. There is no meaning to the deviations of that fit. You just fit. But we gradually started realizing that there might be some sort of an ensemble significance to this problem. So then the easiest thing was to figure out, what is the root mean square fluctuation that we are seeing inside these simulations, and do they correlate well with, the B factors that are reported, or the local resolution that was around 2016 local resolution was computed. Right now, we can also do a Q-score analysis of this and see how does the RMSF match with that. So essentially the uncertainties in fitting, not the uncertainty in structure, these are very two different things. Uncertainty in structure actually has a statistical significant meaning. It has biological relevance. Uncertainty in fitting is something, it's to do with the way you're fitted. So somehow the uncertainty of the fitting matched more or less okay with the resolution. So we were like, okay, fine, we're doing a good job. But then this idea that there can be some statistical mechanics, some probability distributions, log of which can be called an energy function, remained with us. Of course, people can use this tool. It's a very useful tool. We have, popular. So this is the website from which you can download and use this. We have good tutorials and all that. Okay, the next thing is, can we make MDFF better? So one thing that came up, and I want to show that. So in MDFF, let's call phi xs, that's like the experimental density. So most of our, we remain in the density zone. Like once we have gotten the 3D reconstruction, we start our journey from there. If we can go down to the 2D images, if Pilar can help us do that, then that will be great. But till then, we'll live in the 3D densities. So this 3D density, we threshold that in order to do our molecular dynamics simulations. This 3D density can be written using a Gaussian mixture model. And in fact, one can now figure out what is the difference between the 3D density and the Gaussian mixture model. And one comes out with a very simple algebraic form of this difference. Let me also plug in the Gaussian mixture model inside. Let's call it G. And essentially, what we have is, using the Gaussian mixture model, we can rewrite this UEM using 3 terms. The first term is nothing but a restraining potential. It tells us how close our computational reconstructed density is close to the experimental density and a square of that. The second term is actually like a scale density. The third term is weird. The third term here is what we call an error term. If I have to show you this term, the algebraic form of this term is up here. It shows the weights of 2 atoms divided by the width of the, let's say, the half width of the half width of some sort of a distribution function that I'm using, the half width of the Gaussian, and this is the property of the Gaussian. So essentially what this tells me is that inside this U, when we rewrite this potential that was used inside molecular dynamics flexible fitting, but using Gaussian mixture models, there is a weird gravity-like term. It pulls all the atom together in the same place. This was already hidden, this was not explicit, but this GMM basically reformulation of the same potential shows you that, that there is, what were we doing? We were taking a density and we were putting atoms inside the density. We never said 2 atoms should or should not be on top of each other. Somehow, this, of course, we are doing it with molecular dynamics force fields. The force field tells us that the atoms should be far away from each other. So that's the only reason it was safe. Now we do an MDFF without the force fields. This is what happens. So this is an artifact. Yeah. So
do you think this happens in all the mixture models that are around, like the EM?
I don't want to say that, okay. But this at least in the context of MDFF, if you do all of these kind of data-guided MD simulation, not all, like my simulation, so you take this kind of molecular dynamics simulations and remove the force field from the simulation. Simply ask the atoms to be particles and push it inside the density. You get these sort of structures. Of course, force fields are there, that prevents it from happening. But then we wanted a little more, clearer. In fact, then we started doing it on different systems. The errors, in fact, grows with system size. Then the other thing is there are certain side chains for which the errors are most, which are these basically the histones, the phenylalanines, and arginines. So essentially, when you start fitting structures into densities, there were some problems, which then prompted us into doing something that simultaneously got us into this idea of using experimental data with statistical mechanics. So now then, let's write, again, let's use our Gaussian mixture model, use our Gaussian, for a density. Let's say we saw in the first day, we have this density movies. We have like n number of density movies along a trajectory. Let's take all of them and let's make a linear combination of all the movies. And each one of this movie is nothing but a combination of atomic densities. A density can be a Gaussian. For simplicity, let's just choose 2 movies and call it phi b at position B. One is at position B and the other is at position A. And let's make a collective variable that's nothing but essentially the density itself, the difference of the densities, the difference of the sum of the densities. So you take a map, you take the local densities of the map, and you literally sum them up. It's a very simple treatment. There is nothing, there's no rocket science here. And then essentially you create a path along along your densities where, let's say you start from 0 and the last density is 10. You can say 0, 1, 2, 3, 4, 5. Now, is the density path right or wrong? I'm not asking. I'm simply telling I'm translating my density map within a linear variable. Now, a simple way of looking at that is this variable that I've constructed, which is nothing but a sum of atomic densities. So this I goes from 1 to n represents the number of atoms. This is the corresponding atomic density, a weight. So all of this put together is one density map. And if there are zeta k number of density maps along a pathway, then you essentially have a linear combination of density maps. You take any two of them and you say that zeta k is -1. It's essentially the difference. It's essentially the difference map between two densities. Now, if I can use this difference map between the densities as a harmonic potential, like this, again, like the difference map of these two densities can also be written in terms of the cross correlations of the two densities. Let's say I am at a point R that is between A and B, then where I stand in that space is essentially, it's very close to the linear difference between Cc of R with respect to B minus Cc of R with respect to A. I take this object and I make a harmonic spring out of this. Remember, I like making springs. I make force fields. So I can add one more spring to my calculation, which is nothing but this density, exactly. So it's like I'm converting my density difference as a spring constant, essentially as a potential function. In doing so, the first thing, now let's do some mental math. This is my potential. The force is the first derivative of this with respect to position. So what I am doing is, there will be a square of this term, a single of this term, and there's a constant. So the square is nothing but the derivative of cross correlations. So the derivative of cross correlation is very, very different from derivative of the density itself, for the following reason. If I have two minima like this, and if I were to minimize the density, then all my particles would have come to this point, and that would have given me this artifact. But if I'm doing a derivative of cross correlation, the particles will have to be distributed this way, otherwise the cross correlation will also be compromised. So it's essentially a cross correlation driven force that I'm being able to draw. That's out of the first term. The second term, however, if you do the square, that remains a derivative of a density. And the derivative of a density is important because the forces coming from the derivative of a density are long range forces. They can really, like if I have a structure that is really, really bad and a density that is far away, I really need long range forces to bring the structure into the density. So it's a combination of long and short range forces. That's what we ended up creating by creating this sort of a collective variable. And now, then life becomes really easy. What you can do is, as was seen in the previous talk, you can take a reaction progress from one density to another in terms of this collective variable, and you can figure out what is the energy required to deform the density along that. And you can literally find out using classical molecular dynamics how much is the energy of deformation of a density. So now I can do the following. All the machine learning maps that are being created, I can figure out the energy difference of those map deformations and can tell that is this thermally accessible or not? Is this really dynamics or is this biological relevant? Because of course you can have a lot of deformations, but that does not mean that there is any biological relevance to it. There is no but if you can figure out the energy difference between these, then you can do that. Then you can say that this is possible under room temperature. So that's actually the first way forward that we had. Like we converted this entire problem from a fitting problem into a problem of creating a harmonic out of a force field out of the density. So that's the first thing. Any questions? These are simple things. I'll get into a little more complicated things. So, okay. With that also, the other thing is now you can look into things like mole probability scores. Now, all that fight between the atoms that was created for that, bad term, that erroneous term is gone. So the structures become better, and we are hoping to do a whole PDB analysis of this to see can we actually make all the structures in the PDB better by defining them using density as a collective variable. But fine, so this is okay. So the next thing is, okay, now let's try to address the horse in the room. It was so manifold EM. So has been talked about in various ways. So what does it do? So you see this, what does it claim to do? Let's talk about that. So you have this, beautiful density movies. Again, I take the movies as movies. I don't know what do they mean for now. The additional point that the speakers have made here is that they can construct this free energy surfaces, and they can say that when we're moving in the surfaces, this is the corresponding, structural changes that is happening. Now, there are some goods and bads to it. Let me first tell the good things. So, this movie is going to play. So the first thing is, often this gives a molecular dynamics simulator an opportunity of asking the question, what are these big systems doing? Like this big RYR movements. So then you look very locally into these regions and do very long molecular dynamics, and you see that, when this thing is locked with the ions present, then one conformation is more stable. When this ion is gone, then another conformation is more stable. So it, at one level, generates hypothesis. I can't disregard that. So at the level of doing scientific discovery, it gives me a starting point that I would not have gotten otherwise. Just starting from one structure, I would not have gotten otherwise. Similarly for spike, just one very short spike slide. Like essentially, any stationary, submission of spike. So what I'm plotting here is the solvent accessible surface area for different therapeutic targets of spike, as computed from any PDB structure that was submitted to PDB at that point of time, compared to some of the biggest molecular dynamics simulations done by D.E. Shaw, versus versus the ones that we resurrected from the models from manifold EM. We found certain very rare conformations with solvent accessible surface area that are either higher or lower than whatever was experimentally monitored before. So we found some very rare conformations. Now, whether this conformations has any biological sense or not, that's a different story. But manifold EM gives you that. Does it give it to you correctly? That's the next question. And where might be the error? So what are diffusion maps? To start out with, diffusion maps actually are a very solid concept in statistical mechanics. You get into what you call, so this equation is called a Fokker-Planck equation. It's an equation for diffusive dynamics, to simplify that. So a solution of the Fokker-Planck equation is actually written in terms of eigenfunctions. And these eigenfunctions are nothing but collective variables. These are what you call diffusion coordinates. So what diffusion map is doing is, it is projecting your movement in this space of diffusion coordinates. So it is actually a coarse graining methodology, but the coarse grain space is a diffusion distance. So essentially in diffusion map, you are actually monitoring dynamics in the space of dynamics. That's the strength of diffusion map. So normally you'll think of the center of mass of something. That is a geometric variable. In diffusion maps, the variable is actually dynamic. So that's the strength of this object. Now, yeah, question?
So we're using diffusion maps for things that don't have time.
You're using diffusion, yeah, dynamics does not need to have time. In a way, this time that we are talking about here is a matter of, actually what it needs is a sequence, not time. You can use diffusion maps to maintain sequence. And not necessarily time. So now then, or an order. So now this is what Hakim and Peter and Abbas does. They take the snapshots, they select it by orientations, and then they form this manifold. This manifold is made in this space of diffusion maps, of this diffusion coordinates. There's a kind of transform that is used there. This transform is called a Laplace-Bartrami transform, and thereafter, you can once you make this manifold, after this creating of a landscape and all of that, the physics is very clear. There is no problem in the physics. Now there are two problems, as was identified on the first day already. If there are inconsistent orientations, then the manifold will definitely be incorrect. There is no doubt about it. That there has to be, if there are ways in which a rotated and a straight image are considered the same, then this manifold is definitely going to be incorrect. The reason for that is because if I go back, in these eigenfunctions that we're constructing, a simple form of that eigenfunction is basically differences between two states. I'm telling two states that are the same are actually different. So essentially, that is this kind of a kernel, the eigen. Oh, so I should tell this. So this is a simplified version, which is often used in diffusion maps. Turns out the eigenfunction of this particular operator is the same as the eigenfunction of under certain operator is the same as the eigenfunction of this operator here under certain conditions, and that's what is often used. So it would be difficult to kind of, so that problem is there. But let's say somehow we fix that problem. There's an even bigger, I think there's another bigger problem. Once you construct that manifold, let me actually, after that you have to make a decision. Let me show you that decision first. This is a molecular dynamics simulation and doing diffusion maps using diffusion coordinates. One thing that people need to do is they need to decide on how many eigenvectors and eigenvalues of the solution do they need to keep. They have to figure out a spectral gap in this study. And what they find is, so this is a simple 12-alanine example. Here, even here, this gap is so small. If you go to bigger systems, might be the gap is bigger, but you don't know. In traditional use of diffusion maps, that has been, I think, that have been published, these truncations have been essentially brute forced to the first two, and they're gone. Now, the biggest problem is then you're actually missing out information on so much dynamics in your system, which might, so you have used all of your data, yes. You have utilized, so that problem is overcome. But the amount of reduced coordinate that you wanted to extract could have been more. No systematic test is done there. So you're just chopping it off here. And now let me show you the ramification of this in a real molecular dynamics simulation. So again, a small, so we already saw this free energy surfaces. That's what we're after. We want to find, if you get this, then most of the problem in the world is solved. At least some of us feel that way. So now then, we want to figure out minimum free energy pathways. There are some definitions of minimum free energy pathways that we have to keep in mind. Number one is a solution of an overdamped Langevin equation, which is okay. Number two is that it's an energy minima in all dimension barring one. That's a clear definition of minimum free energy pathway. It's not any pathway on the surface. I cannot just draw any pathway on the surface and call it minimum free energy. It will have to be a minima in all dimensions, barring this one dimension where I am seeing the barrier. It will not have any thing in the orthogonal space. Like anything on this sides of the path will actually be a maxima. This will be it will actually have to find, the barriers will have to be along the path. And finally, there's something a little bit more technical. It'll pass through something called an isocommuter surface. Let me not get into that. These are very, very important definitions. If you don't have these definitions, neither free energy nor the pathways, they don't mean anything. Now, often what happens is, there's something called a string simulation in molecular dynamics simulations where, in principle, you can find minimum free energy pathways given endpoint structures. This is also developed. This is developed by a number of people. So what you do is, on this very complicated surface, you start out with a particular trajectory, with a training trajectory, and then this trajectory is morphed into the minimum free energy pathway. Now I am assuming that this trajectory is diffusion map. So actually no, I'm assuming that this trajectory is diffusion map. This is the minimum free energy trajectory. If I take a trajectory coming out of diffusion map, my expectation will be, if I run the string simulations on that, this string is never going to move at all. Why? Because I'm claiming that I've gotten the minimum free energy pathway. So, and essentially I'm claiming that the algorithm, be it diffusion map or any other, cryo-dragon or any other algorithm of heterogeneity, if they are giving me the minimum free energy pathway, then on this free energy landscape, a string simulation will not, it will like stay there like a piece of rock. This thing is not going to move because it is biologically relevant. What happens when we do this with the spike simulation? So with the spike simulation, so this is kind of my pathway in this CC1, CC2 space. Actually, let's forget the upper part, doesn't matter. At every point, I have 10 points on that pathway. This is my original pathway, and this is the drift of my pathway as I do my string simulation. Every point has drifted close to 4 angstroms, and ultimately it has converged somewhere. And this is at 2 different temperatures. So at 310 and at 277, the drifts are lesser, but there's a significant drift of 4 angstroms on every point. So if I'm taking diffusion map guided densities on face value, or for that matter, any other object, they are not sitting on my minimum free energy pathway. Again, one can say that this is not the right comparison, and I agree, because these are not like the same temperatures and things like that. But the thing is, we should not take it on face value. I mean, that's the point. In fact, another thing to one second. I want to make that point even more dramatic. So if you take the length of these pathways, the arc length, this pathway is a very weird contorted shape in this n-dimensional space. The length of this pathway starts out, let's say, 175 angstroms, and this grows, after doing string simulations by 10%. So it is not like what we are seeing in Cryo-EM there. Need not be, at least for this one example, I can't say that, but need not be what we call a biologically relevant or a minimum free energy pathway. It is a treatment of the data, yes, a faithful treatment of the data to the extent we do all the things right. But after that, biology is doing something more to it. So, okay, question.
So basically, you take your 2D diffusion map, and then you look for the minimal free energy path in this space, and then you build 3D structures along the path.
Correct.
And then you launch simulations. So if you had along this path a barrier, like two states and a barrier, wouldn't you expect the guy on the top just to go to the two?
So that's in string simulations. That's a detail of the string simulation. You actually give a constraint so that you don't go that. Okay, so essentially the take home is that, we like, as I said, that there is an issue to infer minimum free energy pathways by only trusting the maps. I think if there is one take home like that I would like to give, that that we should not. But again, this is a very, very expensive computation. Who would do so much? So now then we came up with another way of, let's say, when I talk about a pathway, I'm very, very interested in only the milestones on the pathway, and not necessarily the barriers that I want to overcome. Let's say I give up on the energy barriers on the pathway, and we start doing maximum likelihood calculation. So what is maximum? So we've already seen that here. So what we do is, you have this P as an P of X, probability of X, by knowing this determinant D. So you need to know the position X at a given D. So essentially, again, you have a likelihood and your prior. The prior is nothing but the force fields, all the calculations that you have. And you want to figure out what is your D given X. Now, what we figured out is, if you give up on the idea of not being able to overcome transition barriers, you're simply interested in the energy minima. Most of my ensemble is a number of energy minima and not the barriers at all. Then what we can do is, we can come up with a function, with a probability function that is a function of products of all the restraints. Restraints coming from the experiments and restraints coming from force fields. And exchange those restraints and generate data out of that. That looks a little bit, and essentially, as a part of this restraint, we can introduce this multi-map, the Cryo-EM information. And then it's very simple. You take a density. From there, you don't take the density on face value. You take the secondary structure, the topology, the contacts, etc., whatever information you can get from that density. You have your AlphaFold as your search model. You create a search model, and then using these functions, you start generating structures. I'll just give you a visual example, and then that will possibly help you. So this is, of course, data from Vaz lab, where simultaneously we are using electron tomography as well as electron microscopy data. So we are generating all the constraints from these two data points, and we're imposing that on the simulation. We're not imposing the density explicitly on the simulation. We are taking features of the density and imposing that on the simulation. What that allows us to do is, let's say one more, what that allows us to do is the following. If you impose the density on a structure, you will always get the most probable structure. But if you take the information from the density and impose that on the structure, you will get an ensemble, you will get a population, of which, let's say there is one that is the most probable, one of the minima, but then there are other minimas also along the way. These minima might actually be in a different PDB. And that you can actually determine from the data that is given to you. So by starting out with experimental data from one experiment, you can actually start predicting information that can be seen in possibly other experiments. So if you, again, going back to the multiple maps, if there are multiple maps, now what I can do is, and that's the next example. So what VAR did was, using electron tomography, he offered us this 7 different maps. And not only that, he offered us a distribution of what are the populations for each one of these maps. Now what you do is you start with one map and you do your sampling. Your sampling is not, your structure, see, it's not fitting to the map now. Unlike the previous case where the structures were fitted to the map, you have some probability of a structure that is here, but you have other probabilities of the structure meandering all over. So in principle, if I have 7 maps and these colors are 7 different distributions, I start from each one of them. But then I let my data-guided ensemble generation do the sampling. So I start at a lower angle and my simulation can actually go to a higher angle. Doesn't matter because I'm not just binding it to the most probable structure. I'm generating ensemble. So at every point, I'm generating a data-guided ensemble. And now I reweight all of this and I can reconstruct a free energy profile based on this. And this free energy profile tells me that this spike protein likes to stay in a bent conformation. So essentially, I have not imposed density. I have inferred from density. That's the difference. Because if I infer from the density, I can infer the structure that is fitting the best, but I can also infer other structures. And might be biology can or cannot use it, who knows? But I give my simulation the opportunity of doing it, which is very different from the diffusion map kind of an approach that we were talking about. Essentially, we have to learn inferring things rather than imposing things. Okay, so now I have gone to an ensemble, but still I don't know my pathway. An ensemble gives me a bunch of structures of free energy, but on my free energy surface, where I am and what are the pathways, I still don't know that. I can reconstruct a surface right now by the statistics. So essentially by using these sort of Bayesian inferencing methodologies and experimental data of density, not images, we can reconstruct free energies. That possibly is more easy. But again, what does this free energy mean? So now I take this will be possibly, how much time do I have? I have more time, yeah. So there were no questions. Am I boring you guys a bit too much? Did you guys, okay, what is the thing that you did not understand? I mean, okay, what is the thing that you did understand? Like we're trying to fit structures into densities. Fitting structures into densities is not the whole story, so you have to fit ensembles into densities. The Cryo-EM community has a way of calling something ensemble, namely the density movies or the heterogeneity. Are they real ensembles? I'm questioning that. If they are real ensembles, then the energy distribution of those energy densities should actually make something biological relevant, should mean something. What is the highest barrier of an enzyme? Can anyone tell me in this room? Biology, what is the highest energy value in which biology can operate?
30 kBT, 40.
10 to 30, let's say. So KBT is 0.6 kilocals per mole. So 10 to 30 is any times between 6 to 15 kilocals per mole. Turns out at 15 there's no enzyme that is known that works with energies more than 15 kilocals per mole. How much energy does an ATP, what's the energy currency of life? ATP, everyone knows that, possibly. An ATP breaks 7 to 14 kilocals per mole. So there's a relationship there, like the chemical energy of life is correlated to the function of all the enzymes. And so therefore what I'm trying to create is an energy scale here, that any kind of dynamics should follow that kind of an energy scale. And I think for the most part it is, but not absolutely. We have to do if we start doing some inferencing, then we will be able to get those energies. Okay, now I think this is at least the intellectually most interesting part of the work that I have done so far. We are on a free energy surface. The equation of motion that turns out that can be solved in order to move on an energy surface, let's say we're diffusing on the surface of an energy, is called this Muller-Kautsky equation. So Q, let's call Q like a collective variable, like my position on that position, on the surface. The rate at which I change on that surface depends on the d, the diffusion coefficient, d square q dx square, which is some sort of a variation in position. A weird term v, which I'll talk to you a bit later, and another term called u. So what is happening is, I'm on this surface. I want to go from point A to point B. And what I'm doing is, I want to move towards point B and have the knowledge of point B. That's very, very important to know. So essentially, the dynamics of that object can be determined using this Molokowski equation, where there's a very interesting term that comes into the picture. This V term has a double derivative of u, which is actually a single derivative of force, and a single derivative of force whole square. What is a double derivative of force? Something like a jerk, that kind of a feeling. So essentially, if you want to really move on the surface, you can actually solve this equation, and you can get to the surface. Actually, a form of this equation I've shown you for diffusion maps. In that diffusion map, we have seen an eigenfunction solution of this particular problem. Now let me show you a Feynman's path integral solution of this problem. So if you consider time to be a continuous variable, which people have, that was Feynman's discovery, like time was a continuous variable, and in fact he even worked on imaginary time, then you can write the solution Q of this partial differential equation in this form. Now, sorry, Q was the probability, I'm so sorry, I do. So it's the motion of probability on the surface of, it's the probability of finding a point on this free energy surface. So essentially you can solve for Q at any given point of time by writing this Feynman's path integral. So this path integral again has a derivative of potential, U is the potential with respect to time, has a derivative of potential with respect to position, which is force, and a derivative of force. Now there's this famous thing called Jarzynski's equality. If I have 2 points, if I have 2 points on the free energy surface, then the work that is taken, that it requires me to go from point A to point B, the average of that work can be correlated to the free energy difference of those 2 points. So now then, you take this equation and you put in this form of the time-dependent probability into this equation. And what you get is a form of a path integral dependent form of Jarzynski's equality. So essentially, Jarzynski's equality is very interesting. This work is a non-equilibrium quantity. Free energy is an equilibrium quantity. This is the first equation that connects a non-equilibrium quantity with an equilibrium quantity. And what we have found is a path integral formulation of figuring out this non-equilibrium quantity. So essentially, what we see is that this exponential of work, which is the work of deformation, can be written in terms of S, which is an action. Now let's look into this action. As I said, the action means that if I go from point A to point B, I have to lower my energy. This term goes to 0. I have to lower my jerk, which is very, very important. People always think about energy, but there's a derivative of energy that's very, very important to think about, which is force. I have to lower my force, and I have to go towards my final action. So what one can do now is one can create a PPO algorithm, a reinforcement learning algorithm. Question?
Shouldn't that be a phase in the Feynman integral?
I think, okay, yeah. So there is a phase in the Feynman integral,
No,
but this is
an overall I? No?
You mean like, no, so like it's the phase is, okay, there's an assumption that the total phase is conserved, so it's a constant. In these kind of simulations, when you're moving when you're diffusing on a free energy surface, the basic assumption is that the phase space you are in, it's essentially a Hamiltonian system. It's a linear response regime. So the phase will be there, but that's a constant. Now then what we can do is, we can start training a reinforcement learning algorithm, so what's a reinforcement learning algorithm? We have an agent, that agent moves. After that agent moves, you give that agent a reward. Based on positive or negative reward, the agent learns to make that move or not that move. So what we have done is, we have said that this reward for the agent is the action function L, is the Feynman action function L. So an agent would move only if it goes to lower energy, only it goes to point number B, or it goes to a low force pathway, and a combination of all of that. So essentially you start from point A, the agent would start moving, you give it a grid, the agent would start moving on that grid, and it would get stuck somewhere, because here it will find a barrier. So the energy part of the Feynman path integral would complain. Might be it will have 2 equal paths, but the force path, it will take that path where the force part will be important. And so essentially, and this, of course, the reward is computed based on cryo-electron densities. So with that, then now we can start doing very, cool things. Essentially, you're on one point. Let's say we start with alanine dipeptide, and we want to go to another point. And this is a free energy surface that is known to us. We can have this reinforcement learning algorithm to go from A to B, and gradually, after a certain number of iterations, first it will start going through very high energy transitions, and then gradually the energy of the transition goes down. Question?
What is the dimension of this landscape?
Of this landscape, right. So for this particular case, you have a phi and a psi. There are two angles here. And currently, this is now, I've promised you that this will move on a surface that is trained by the experimental data. On this is not the experimental data. On this, in this particular case, where is my action functional? Here, so this action functional here, this U is purely dihedral angles, but that's one example. Next thing is, okay, very good. Next thing is, remember I showed you this adenylate kinase movie? Now what we have done is, so this was the movie. I had gotten the free energy, but I did not know where exactly I was. Now the underlying free energy landscape of this object is known. I started from here. I have given it a target that is here. So this is a closed state. This is an open state. For this, I have a crystallographic density. And what I'm doing is I'm pulling my structure starting from here towards this crystallographic density. And what my reinforcement learning is doing is, it is optimizing for action that is going from here to here. Had I done a normal MDFF or pulling, it would have, it would have gone straight. But because it is learning the minimum energy landscape, or at least the minimum action landscape, it is going here and getting stuck so many times. And might be trying this movements before it goes here. Now let me show you the next example, which I'm very, very happy about. Alternate axis mechanism. So an alternate axis mechanism is a mechanism in biology where essentially a protein takes an ion from one side, and then it closes, goes to an occluded state, and then finally opens up a state. So essentially this is an intermediate. So if you think of a movie, might be one of the tests of the machine learning algorithms can be, if there is normally if you have a channel or a transporter in action, you're seeing an ensemble of all of these three things. And can you actually resolve all of these three? So what we did is we said that, okay, let's start with an experimental data. This is crystallographic data still, of this object here. And let's start with a starting model from here. This is my point A, this is my point B. Can I go from A to B? And what happens? What's the pathway? Of course, in the two other examples I gave you, I knew the answer because I knew the underlying fringe landscape. Here, I don't know the answer. So this is my point A, this is my point B. A straightforward molecular dynamics pulling simulation, for example, will take me here. However, my reinforcement learning algorithm starts from here, takes me on the left, and then brings me down. Now, this is a very interesting point. This point is actually what you call an occluded state, the intermediate. My machine learning did not know about this intermediate. It simply had the data of the end point, and it was working on minimizing the action. So it turns out that the minimum action route takes it through the intermediate. That was not known to me. So essentially, even though I don't know my underlying landscape on this, I'm visiting certain structures that are experimentally verified, but I haven't used that in my calculation. I haven't used that in my model. My learning has found that for me. So this can safely be from here on a cryo-EM density. We'll have to do that. And we can make these moves and make this. So essentially, that is the way we can start, possibly one of the ways we can start getting pathway information, not just free energy, from cryo-EM images. And yeah, with that, I would like to stop. I have just 2 slides more. I want to just make sure that, okay, I had 2 more. See, I made 50 slides. So I really want to acknowledge there's a community of people, as Pilar mentioned. We are not the only people doing this. If you know any one of these people, these are very good people to work with. So do find out people who are in your vicinity, and these kind of ensemble. Not everything is an ensemble method, but molecular dynamics with cryo-EM is very prevalent. So that, and I had a wish list for the cryo-EM community, which I think part of that we already know, is that if there can be more out of equilibrium measurements, then that would really help us in terms of doing with molecular dynamics simulations. Realistic solutions of the forward problem, I think that's very important. Like giving structure, it's fine, but from structure to image, so that one can start inferring things. The realistic solutions, if you don't have realistic solutions, we can't put it inside molecular dynamics. And yeah, the first part is okay, we can handle that. But yeah, with that then, thank you. Thanks for your patience, and thanks for being such a nice audience. Thank you.